A sundial is a device that tells the time of day by the apparent position of the sun in the sky. In the narrowest sense of the word, it will consist of a flat plate, the dial, and a gnomon which will throw a shadow onto the surface. Lines marked onto this surface will indicate the time of day. The style is the time-telling edge of the gnomon, though a single point or nodules may be used. As the sun appears to move across the sky, the shadow edge aligns with different hour lines. The gnomon may be a thin rod, a wire, or an elaborately decorated metal casting. The style must be parallel to the axis of the Earth's rotation to remain accurate throughout the year. The style's angle from the horizontal is equal to the sundial's geographical latitude. In a broader sense, a sundial is any device that uses the sun's altitude or azimuth to show the time. It is common for inexpensive mass-produced decorative sundials to have incorrect hour angles, which cannot be adjusted to tell correct time. Sundials are valued as decorative objects, as literary metaphors, and as object of mathematical study. Introduction. There are different types of sundials. Some sundials use a shadow or the edge of a shadow, while others use a line or spot of light to indicate the time. The shadow casting object, known as a gnomon, may be a long thin rod, or other object with a sharp tip or a straight edge. Sundials employ many types of gnomon. The gnomon may be fixed or moved according to the season. It may be oriented vertically, horizontally, aligned with the Earth's axis, or oriented in an altogether different direction determined by mathematics. With sundials using light to indicate time, a line of light may be formed by allowing the sun's rays through a thin slit or focusing them through a cylindrical lens. A spot of light may be formed by allowing the sun's rays to pass through a small hole or by reflecting them from a small circular mirror. Sundials also may use many types of surfaces to receive the light or shadow. Planes are the most common surface, but partial spheres, cylinders, cones and other shapes have been used for greater accuracy or beauty. Sundials differ in their portability and the need for orientation. The installation of many dials requires knowing the local latitude, the precise vertical direction, and the direction to true north. Portable dials are self-aligning. For example, it may have two dials that operate on different principles, such as a horizontal and analematic dial, mounted together on one plate. In these designs, their times agree only when the plate is aligned properly. Sundials indicate the local solar time, unless corrected for some other time. To obtain the official clock time, three types of corrections need to be made. Firstly, the orbit of the Earth is not perfectly circular and its rotational axis not perfectly perpendicular to its orbit. The sundial's indicated solar time thus varies from clock time by small amounts that change throughout the year. This correction, which may be as great as 15 minutes, is described by the equation of time. A sophisticated sundial, with a curved style or hour lines, may incorporate this correction. Often instead, simpler sundials are used, with a small plaque that gives the offsets at various times of the year. Secondly, the solar time must be corrected for the longitude of the sundial relative to the longitude of the official time zone. For example, a sundial located west of Greenwich, England, but within the same time zone, shows an earlier time than the official time. It will show noon after the official noon has passed, since the sun passes overhead later. This correction is often made by rotating the hour lines by an angle equal to the difference in longitudes. Lastly, to adjust for daylight saving time, the sundial must shift the time away from solar time by some amount, usually an hour. This correction may be made in the adjustment plaque, or by numbering the hour lines with two sets of numbers. Apparent motion of the sun. The principles of sundials are understood most easily from the sun's apparent motion. The Earth rotates on its axis, and revolves in an elliptical orbit around the sun. An excellent approximation assumes that the sun revolves around a stationary Earth on the celestial sphere, which rotates every 24 hours about its celestial axis. The celestial axis is the line connecting the celestial poles. Since the celestial axis is aligned with the axis about which the Earth rotates, the angle of the axis with the local horizontal is the local geographical latitude. Unlike the fixed stars, the Sun changes its position on the celestial sphere, being at a positive declination in spring and summer, and at a negative declination in autumn and winter, and having exactly zero declination at the equinoxes. The Sun's celestial longitude also varies, changing by 1 complete revolution per year. The path of the Sun on the celestial sphere is called the ecliptic. The ecliptic passes through the 12 constellations of the zodiac in the course of a year. This model of the Sun's motion helps to understand sundials. If the shadow-casting gnomon is aligned with the celestial poles, its shadow will revolve at a constant rate, and this rotation will not change with the seasons. This is the most common design. In such cases, the same hour lines may be used throughout the year. The hour lines will be spaced uniformly if the surface receiving the shadow is either perpendicular or circular about the gnomon. In other cases, the hour lines are not spaced evenly, even though the shadow rotates uniformly. If the gnomon is not aligned with the celestial poles, even its shadow will not rotate uniformly, and the hour lines must be corrected accordingly. The rays of light that graze the tip of a gnomon, or which pass through a small hole, or reflect from a small mirror, trace out a cone aligned with the celestial poles. The corresponding light spot or shadow tip, if it falls onto a flat surface, will trace out a conic section, such as a hyperbola, ellipse or a circle. This conic section is the intersection of the cone of light rays with the flat surface. This cone and its conic section change with the seasons, as the Sun's declination changes. Hence, sundials that follow the motion of such light spots or shadow tips often have different hour lines for different times of the year. This is seen in shepherd's dials, sundial rings, and vertical gnomons such as obelisks. Alternatively, sundials may change the angle and/or position of the gnomon relative to the hour lines, as in the analemmatic dial or the Lambert dial. History. The earliest sundials known from the archaeological record are the obelisks and shadow clocks from ancient Egyptian astronomy and Babylonian astronomy. Presumably, humans were telling time from shadow lengths at an even earlier date, but this is hard to verify. In roughly 700 BC, the Old Testament describes a sundial, the dial of Ahaz, mentioned in Isaiah chapter 38 verse 8 and 2 Kings. The Roman rite of Attribution lists dials and shadow clocks known at that time. A canonical sundial is one that indicates the canonical hours of liturgical acts. Such sundials were used from the 7th to the 14th centuries by the members of religious communities. Italian astronomer Giovanni Padovani published a treatise on the sundial in 1570. In which he included instructions for the manufacture and laying out of mural and horizontal sundials. Giuseppe Biancani's Constructio Instrumenta ad Horologia Solaria discusses how to make a perfect sundial. They have been commonly used since the 16th century. Terminology. In general, sundials indicate the time by casting a shadow or throwing light onto a surface known as a dial face or dial plate. Although usually a flat plane, the dial face may also be the inner or outer surface of a sphere, cylinder, cone, helix, and various other shapes. The time is indicated where a shadow or light falls on the dial face, which is usually inscribed with hour lines. Although usually straight, these hour lines may also be curved, depending on the design of the sundial. In some designs, it is possible to determine a date of the year, or it may be required to know the date to find the correct time. In such cases, there may be multiple sets of hour lines for different months, or there may be mechanisms for setting, calculating the month. In addition to the hour lines, the dial face may offer other data, such as the horizon, the equator and the tropics, which are referred to collectively as the dial furniture. The entire object that casts a shadow or light onto the dial face is known as the sundial's gnomon. However, it is usually only an edge of the gnomon that casts the shadow used to determine the time. This linear feature is known as the Sundial Style. The style is usually aligned parallel to the axis of the celestial sphere, and therefore is aligned with the local geographical meridian. In some sundial designs, only a point-like feature, such as the tip of the style, is used to determine the time and date. This point-like feature is known as the sundial's nodules. Some sundials use both a style and a nodules to determine the time and date. The gnomon is usually fixed relative to the dial face, but not always. In some designs such as the analematic sundial, the style is moved according to the month. If the style is fixed, the line on the dial plate perpendicularly beneath the style is called the substyle, meaning below the style. The angle the style makes with the plane of the dial plate is called the substyle height, an unusual use of the word height to mean an angle. On many wall dials, the substyle is not the same as the noon line. The angle on the dial plate between the noon line and the substyle is called the substyle distance, an unusual use of the word distance to mean an angle. By tradition, many sundials have a motto. The motto is usually in the form of an epigram, sometimes somber reflections on the passing of time and the brevity of life, but equally often humorous witticisms of the dial maker. A dial is said to be equiangular if its hour lines are straight and space equally. Most equiangular sundials have a fixed gnomon style aligned with the Earth's rotational axis, as well as a shadow-receiving surface that is symmetrical about that axis. Examples include the equatorial dial, the equatorial bow, the armillary sphere, the cylindrical dial and the conical dial. However, other designs are equiangular, such as the Lambert dial, a version of the analematic dial with a movable style. Sundials in the Southern Hemisphere. A sundial at a particular latitude in one hemisphere must be reversed for use at the opposite latitude in the other hemisphere. A vertical direct south sundial in the Northern Hemisphere becomes a vertical direct north sundial in the Southern Hemisphere. To position a horizontal sundial correctly, one has to find true north or south. The same process can be used to do both. The gnomon, set to the correct latitude, has to point to the true south in the Southern Hemisphere, as in the Northern Hemisphere it has to point to the true north. Also, the hour numbers go in opposite directions, so on a horizontal dial they run anti-clockwise rather than clockwise. Sundials which are designed to be used with their plates horizontal in one hemisphere can be used with their plates vertical at the complementary latitude in the other hemisphere. For example, the illustrated sundial in Perth, Australia, which is at latitude 32 degrees south, would function properly if it were mounted on a south-facing vertical wall at latitude 58 degrees north, which is slightly further north than Perth, Scotland. The surface of the wall in Scotland would be parallel with the horizontal ground in Australia, so the sundial would work identically on both surfaces. Adjustments to calculate clock time from a sundial reading. The most common reason for a sundial to differ greatly from clock time is that the sundial has not been oriented correctly or its hour lines have not been drawn correctly. For example, most commercial sundials are designed as horizontal sundials as described above. To be accurate, such a sundial must have been designed for the local geographical latitude and its style must be parallel to the Earth's rotational axis. The style must be aligned with true north and its height must equal the local latitude. To adjust the style height, the sundial can often be tilted slightly up or down, while maintaining the style's north-south alignment. Summertime correction. Some areas of the world practice daylight saving time, which shifts the official time, usually by 1 hour. This shift must be added to the sundial's time to make it agree with the official time. Time zone correction. A standard time zone covers roughly 15 degrees of longitude, so any point within that zone which is not on the reference longitude will experience a difference from standard time equal to 4 minutes of time per degree. For illustration, sunsets and sunrises are at a much later, official, time at the western edge of the time zone, compared to sunrise and sunset times at the eastern edge. If a sundial is located at, say, a longitude 5 degrees west of the reference longitude, its time will read 20 minutes slow, since the sun appears to revolve around the Earth at 15 degrees per hour. This is a constant correction throughout the year. For equiangular dials such as equatorial, spherical or Lambert dials, this correction can be made by rotating the dial surface by an angle equaling the difference in longitude, without changing the gnomon position or orientation. However, this method does not work for other dials, such as a horizontal dial. The correction must be applied by the viewer. At its most extreme, time zones can cause official noon, including daylight savings, to occur up to 3 hours early. This occurs in the far west of Alaska, China, and Spain. For more details and examples, see skewing of time zones. Equation of time correction. Although the Sun appears to rotate nearly uniformly about the Earth, it is not perfectly uniform. This is due to the ellipticity of the Earth's orbit and the tilt of the Earth's rotational axis relative to the plane of its orbit. Therefore, sundial's time varies from standard clock time. On 4 days of the year, the correction is effectively zero. However, on others, it can be as much as a quarter hour early or late. The amount of correction is described by the equation of time. This correction is universal. It does not depend on the local latitude of the sundial. It does, however, change over long periods of time, centuries or more, because of slow variations in the Earth's orbital and rotational motions. Therefore, tables and graphs of the equation of time that were made centuries ago are now significantly incorrect. The reading of an old sundial should be corrected by applying the present-day equation of time, not one from the period when the dial was made. In some sundials, the equation of time correction is provided as a plaque affixed to the sundial. In more sophisticated sundials, however, the equation can be incorporated automatically. For example, some equatorial bow sundials are supplied with a small wheel that sets the time of year. This wheel in turn rotates the equatorial bow, offsetting its time measurement. In other cases, the hour lines may be curved, or the equatorial bow may be shaped like a vase, which exploits the changing altitude of the Sun over the year to effect the proper offset in time. A heliochronometer is a precision sundial first devised in about 1763 by Philip Hahn and improved by Abbe Guyauque in about 1827. It corrects apparent solar time to mean solar time or another standard time. Heliochronometers usually indicate the minutes to within 1 minute of universal time. The Sunquest sundial, designed by Richard L. Schmoyer in the 1950s, uses an analemic-inspired gnomon to cast a shaft of light onto an equatorial timescale crescent. Sunquest is adjustable for latitude and longitude, automatically correcting for the equation of time, rendering it as accurate as most pocket watches. An analemma may be added to many types of sundials to correct apparent solar time to mean solar time or another standard time. These usually have vowel lines shaped like figure eights, according to the equation of time. This compensates for the slight eccentricity in the Earth's orbit and the tilt of the Earth's axis that causes up to a 15-minute variation from mean solar time. This is a type of dial furniture seen on more complicated horizontal and vertical dials. Prior to the invention of accurate clocks, in the mid-17th century, sundials were the only timepieces in common use, and were considered to tell the right time. The equation of time was not used. After the invention of good clocks, sundials were still considered to be correct, and clocks usually incorrect. The equation of time was used in the opposite direction from today, to apply a correction to the time shown by a clock to make it agree with sundial time. Some elaborate equation clocks, such as one made by Joseph Williamson in 1720, incorporated mechanisms to do this correction automatically. Only after about 1800 was uncorrected clock time considered to be right, and sundial time usually wrong. So the equation of time became used as it is today.